The wonderful world of stereochemistry. Can you believe it? It is back. It is here to greet you once again, and stereochemistry wants to be your friend. So I hope that you want to be stereochemistry's friend, because we're going to spend quite some time on reviewing and learning stereochemistry when it concerns the world of carbohydrates. These things are very important. So I want to go back and I want to talk about what stereochemistry meant back in the day, and maybe do a quick review on what the R form was and what the S form was, and make sure that we can at least classify something that way before we go any further into the world of carbohydrates, because bigger molecules, they just get nastier, they get a little hairier, so we're going to have to do a little bit of routine maintenance grooming work on them to make sure that stereochemistry really makes sense. So let's go back to the world of stereochemistry. Stereochemistry was basically a fancy way to talk about structures in a 3D environment. That's what we were after, right? These structures take on a 3D structure. They are actually real things that take up some space, not just a structure on a sheet of paper. And the way that the groups are oriented are very important. So orientation is what we're going to be looking at here. And we said that there were two types of orientation around a center. And most of the time these centers were carbons, so we called them the center carbon. And one version of that was the R, which stood for rectus, which meant right-handed. And the other one was S, which stood for sinister, and that was left-handed. So I'm a very sinister person. I'm a left-handed person, right? So I'm the S form of the orientation, and you might be the R form of the orientation if you're writing with the right hand. So R and S orientation, they're going to be coming back. So notice the careful words that I said. On the center. So what happens is that we have a center atom here, and in order for R and S to take place, if you go back and review the world of stereochemistry, you're going to see that there are four groups that are going to be on here, right? Four groups on the center. And these four groups have to be different. That's the number one thing that you have to take away. The groups that are attached to the center atom must be different. Okay, so what does that mean? Well, let's say this is my center atom, and let's say this is a hydrogen, and this is a hydrogen, and this is an OH group, and let's say that this is a CH2OH group out here. All right, now I'm going to draw that the proper way. It's the carbon that gets hooked up to the carbon, and the hydrogens are on that carbon, and then we have an OH group. So you got to kind of look at it backward for a minute. All right, well, this doesn't really show us any orientation. There's no R and there's no S, and the reason is because two groups that are attached to the center here, they are the same, and those are the hydrogens. So this will not work as far as R and S go. They have to be completely four different groups. Well, if there are two hydrogens there, there's no R and S. If there's two OH groups that are there, there's no R and S. If there's two CH2OH groups on that carbon, well, there's no R and S. They really do have to be different, all four of them. So let's change one of these, and let's just erase this and put maybe a CH3 group here. Now, there are all four different groups, and those are attached to the center, and this center has a very special word that we use to describe it, and that word was called chiral. So this is a chiral carbon if this atom is a carbon in the center. So now we can talk about and remember what a chiral carbon was. A chiral carbon in a molecule is a carbon that has four different groups attached on it. Well, the story, the take-home message here, is that if you look at all of the carbohydrate structures, you are going to be finding chiral carbons all over the place. There's carbons that have 4 different groups attached, and because of that, we see some chirality. And if we see chirality, then we see stereochemistry. So carbohydrates do have a R form, and carbohydrates do have a S form. Well, let's start with the simplest carbohydrate that we can have, and this simplest carbohydrate basically is going to be a C double bond OH, right? So this is an aldehyde, so it's an aldose, and off of this carbon is another carbon that might have a hydrogen on it, and if that has a hydrogen, it must also have an OH group on it. And then off of that carbon is a CH2OH group. Now, I've drawn it this way because I want you to get accustomed to looking at carbohydrates in different forms, right? Most of the time when we draw these carbohydrates, we draw the backbone straight up and down. And I'm going to do that here for a minute. But at the same time, I want you to realize that these carbohydrate structures, they're really no different than structures that you've drawn previously in past courses. I mean, this is a traditional type of structure that we've always seen as far as the aldehyde functional group goes, and we have an OH that's a substituent that hangs off of that carbon. Well, this is an accepted structure. I can draw that structure that way if I want. Or what we traditionally see in biochemistry is the actual carbon backbone drawn up and down like this. So this carbon has a double bond O and an H on it. There's the aldehyde group. This center carbon has a hydrogen and an OH group on it, so I'll do a OH here and an H there. And then this ending carbon has 2 hydrogens and an OH group on it as well. So we'll do a CH2, so 2 hydrogens and an OH group there. So that's the traditional way that we see carbohydrates. That's how we've been drawing them. That's how you'll see them in the textbook. I just want you to keep in mind, however, that these two structures represent the same thing. The only difference is that this one's drawn kind of on its side compared to the one that we've seen so far over and over that's here. Okay, so now let's apply the definition of chiral to these carbons. So I want to start off with carbon number 1, and carbon number 1 is up here at the top. And I want to determine and put a box around the carbons that are chiral, if I have any. And if I take a look at carbon number 1 is not a chiral carbon because there's not 4 groups that are attached to it. We only have 3, right? We have the hydrogen here, and we have the oxygen there, and then we have this huge big long group down here that's connected to it. So number 1 carbon, that is not a chiral carbon. There's no 4 different groups attached to it. If I go to the second carbon, I do have 4 groups attached to this carbon. Now I need to compare to see if they're different. Well, one side is a hydrogen, one side is an OH group, one side is this CH2OH group, and then the other side is this C double bond OH group up at the top. So there are 4 groups here. So that means carbon number 2 is a chiral carbon. So ta-da, we found it. And now I want to take a look at the third carbon. The third carbon, we do the same thing. Are there 4 groups? And the answer is yes. There's 4 bonds that are there. Now, are the groups different? Well, on this third carbon, I see an OH group, and then I see the CHOH, C double bond OH group, this entire thing up here at the top. That's different. But to the left and to the right, I see both of these as being hydrogens, and they are the same group. So because of that, carbon number 3 is not a chiral carbon. So this is the simplest chiral carbon that we have, or chiral, I guess I don't need to say carbon, but I need to say carbohydrate here. So this is the simplest chiral carbohydrate that we have that's in existence. This is a triose because there's 3 carbons. It's a aldotriose because there's an aldehyde functional group, and we do see some chirality around the center carbon. So that means that this carbon in the center, this carbon has a R form and it has a S form. And we need to talk about the difference here because Mother Nature is very picky. And Mother Nature knows it's in her best interest to streamline everything that your body needs to make it work. The less paperwork, the less headache. So what that basically means is that with these carbohydrates and these chiral carbons, we will only see one that is biologically active. Is it the R form, the right-handed one? Is it the S form, the left-handed one? Well, that we'll find out in the next video. So stay tuned. If you're curious, find out what happens after the break.